Hello everybody, my name is Jonas, and today we're going to talk about automated machine learning for tabular, text, and image data. In particular, we're going to focus on practical, subtle implementation issues in this area and how to quickly get started on your own datasets using a tool called AutoGluon. What you will learn in this tutorial includes topics such as how to quickly and easily produce high accuracy models for standard supervised learning problems like classification and regression involving data that might be of tabular format, meaning it lives in tables like Excel files, CSV files, or in databases. It may be text data such as sentences, paragraphs, or entire documents, or it may be image data that you might find from cameras. The underlying topics that we will cover include the principles that enable this automation and the user interface aspects that enable easy-to-use systems. We will not cover the technical details of how individual ML models work, the math behind them, convergence guarantees, nothing like that. Instead, we are going to focus on how to best use models in an overall ML pipeline and how to best combine them or integrate them in the most powerful way in this overall pipeline that goes from raw data to highly accurate predictions. So first, let's talk about the state of machine learning today. One thing you might have seen is that it often requires expert data scientists or PhDs to do right. This is because it's extremely brittle. Many machine learning systems were deployed with specific tricks such that when, say, the original author of the system leaves your company, nobody wants to change the system anymore because they don't quite fully understand how it works, and small changes can drastically alter its behavior. Furthermore, small changes to the data can lead to the system crashing because it can no longer handle some new properties that are appearing in your new data. This is particularly an issue for systems that need to be retrained, say, every night as you have new data being collected. Finally, machine learning today involves many tricks. This means even an expert data scientist who's implementing an ML pipeline from scratch needs to remember to add all these tricks in order to really get the best accuracy. This is obviously not a scalable solution and requires re-implementing many of these same tricks over and over again. Furthermore, given a new data set, maybe only some subset of these tricks are actually relevant to the data set. And it would be nice to have an automated system that can just identify this and apply these tricks automatically. The ideal machine learning system we envision is one in which you merely specify the time it should run for, the evaluation metric that you care about, that you'll basically evaluate your predictions according to, and certain constraints that you might have about the setting in which it will be used for inference. For example, you may say that your system can only take 1 millisecond to produce predictions if you're doing inference in an extremely time-constrained setting. In real time, for example, if your system is running on some kind of vehicle. The ideal system can just be run on raw data and it will figure out for itself what are good models. Giving such a system more compute resources and longer runtimes means you should see the performance start going up automatically. That means you can just let the system start running, walk away from your computer, check on it in an hour, see what the accuracy is, check on it in a day, and the accuracy should be much better. This is the goal of automated machine learning, is to build such a system. Many people have proposed various definitions of AutoML, including, is it hyperparameter-tuning? Is it neural architecture search? Is it selection of a model? In this tutorial, we're going to take a really broad definition. We're going to say AutoML is any system whose input is raw, unprocessed data, and whose output is a model or some kind of Python or object in your favorite programming language of choice that can produce accurate predictions on new data. The key is this process happens entirely without user intervention. You just specify maybe those 3 ingredients I previously mentioned, such as how long do you want the system to run, what metric do you care about, any other kind of constraints you have that you want to impose on the system, and the system will automatically translate raw data into highly accurate predictions. So what's the human role in automated ML? Our goal in automated machine learning is to free data scientists and analysts to focus on higher layer level considerations. Without AutoML, these people have to spend a ton of time choosing models, overseeing their training, making sure everything is working, pre-processing their data, splitting it into evaluation or validation sets and training sets, manually tweaking hyperparameters in an effort to kind of boost their accuracy, but in a really cumbersome fashion, and then repeatedly checking validation metrics to select models or maybe figure out how they might combine different models together. With AutoML, these analysts can instead focus on higher level considerations like figuring out what metrics are actually appropriate for my domain for actually solving my problem of interest. How should I be translating the predictions of my system into real decisions that will impact, say, users if I have an app? How can I best leverage domain knowledge to imbue my machine learning system with domain knowledge, either by encoding this in the data or somehow modifying the resulting predictions of the system based on domain knowledge? And finally, what data should I be using and how should I be formatting this data appropriately for supervised learning in the first place? We think that analysts will be much better off spending their time on these higher level considerations rather than managing the technical details of individual models training just in an effort to, squeeze out a few percentage points of accuracy from these models. Let's talk about some AutoML tools now. Here we're going to talk mainly about open source AutoML tools where you can download the source code, run it yourself, and modify it as you see fit. The first set of tools we will talk about briefly are those designed for tabular data sets. The first of these tools, AutoWeka, was really the first AutoML tool to consider the problem of combined model and hyperparameter selection. This toolkit introduced the idea of Bayesian optimization to select models and their hyperparameters from the Weka machine learning Java library. It was followed up by AutoScikit-learn, which is an AutoML system built around models in the popular scikit-learn library. AutoScikit-learn introduced a few cool tricks, such as more efficient hyperparameter tuning through multi-fidelity approaches and meta-learning, in which they learn which hyperparameters tend to work well on which kind of data sets over large repositories of data sets. In addition, AutoSklearn introduced the idea that strict time management is very important in an AutoML system when it has to run under user-specified time constraints. By very carefully managing time, AutoScikit-learn has managed to win a number of AutoML competitions. The third system we will talk about is Teapot. It's a tree-based evolutionary optimization system that optimizes full machine learning pipelines through an evolutionary algorithm. These pipelines include pre-processing steps to transform the data appropriately, as well as modeling steps to select models and their hyperparameters. By evolutionary algorithm, we mean this system starts with some randomly constructed pipelines where they randomly choose some pre-processing steps and some random machine learning models with random hyperparameter settings on top of those, and see what the resulting performance is. Then they start combining the pipelines that tended to perform well with the machine learning algorithms that tended to perform well in novel combinations through what's called selection. Finally, once they've selected these top pipelines, they begin randomly mutating them to create new pipelines that have slight alterations. For example, they might change one aspect of the pre-processing stage, one aspect of the modeling stage, or one hyperparameter in these models, and then they will again repeat this process. The final tool we'll talk about on the tabular data side in the open source world is H2O's AutoML. This is a very popular AutoML tool that has been widely used on Kaggle and by data scientists in companies. It has a very nice user interface, and it is quite straightforward to run. Behind the scenes, this tool actually isn't necessarily as sophisticated as some of these other tools I mentioned. It simply uses random search to search for the hyperparameters that would work best for its models, and rather than considering a large suite of models through which it randomly searches, it only considers a smaller set of known high-quality models. Now let's talk about some open source AutoML tools for text data. The first of these is AutoKeras. This is an AutoML wrapper around the popular Keras library. If you're familiar with Keras, it basically took what used to take hundreds of lines of code in TensorFlow to write and boiled it down to about 12 lines. So in TensorFlow, whenever you wanted to train a neural network, you had to define the neural network at a very low level of detail, and then you had to train it by writing a batching function that read in batches of data, updated your model's parameters based on these batches of data, etc. With AutoKeras, they've abstracted this away, and you can define a model in just 10 lines of code. You just say, what kind of layers do I want my model to have? And then you just call fit on this model. With AutoKeras, they've abstracted this even further, such that you only need to call fit, and it will try and choose an appropriate model under the hood for you. This library is mainly focused around deep learning, though, meaning it is not as well suited for many tabular datasets where deep learning models are not necessarily the best. Raza is an AutoML library for text data that is mainly intended for chatbots. Under the hood, it uses long short-term memory networks and transformer models, which are among the state-of-the-art models for text data in today's natural language processing community. Ludwig is a model that is suited for entirely code-free automated machine learning. That means the user doesn't even have to write code. They just need to point to their text input and their outputs, which may be numbers or categories or even text fields themselves. So it can do tasks like machine translation, where the input would be one sentence in one language and the output would be sentences in another language. And this is what's known as sequence-to-sequence learning in the machine learning community. Finally, a very popular library today for natural language processing is Hugging Face, which implements many, many variants of state-of-the-art transformer networks that have really come to dominate this area. Hugging Face offers an AutoModels submodule that implements some basic AutoML functionality, although it doesn't really go all the way to fully pre-processing your data for you. Now let's talk about some AutoML tools for images. First tool we're going to talk about is Microsoft's NNI toolkit, which is designed to do neural architecture search. This means, given an image data set, everybody knows nowadays the best models will be convolutional neural networks. However, there's now hundreds to thousands of variants of convolutional neural networks that have each been designed through painstaking care, primarily on just a few very popular benchmark datasets that almost everybody in the computer vision community uses, including ImageNet, CFAR, etc. However, why should models, or neural networks specifically, whose architectures were designed to work well on these datasets, generally be the best architectures possible, especially for your own dataset that might not have similar statistics to these datasets? This library uses neural architecture search to actually create new neural architectures that might be better suited for your own dataset. The next library we'll talk about is AutoPyTorch, which is an AutoML wrapper around the popular PyTorch library. PyTorch is another deep learning framework like TensorFlow or MXNet that has become quite popular in recent times. That said, PyTorch models still require a lot of user finicking, specifying hyperparameters, tweaking hyperparameters to really get good accuracy out of these models. AutoPyTorch mainly aims to improve the hyperparameter optimization aspects of dealing with PyTorch models, but does not focus as much, again, around the pre-processing aspects of the ML pipeline. Finally, we note that AutoKeras, like handling text data, can also handle image data in a similar fashion, and it provides some built-in models, some built-in convolutional neural networks specifically to handle such data. Now that we've covered some of the open source tools, let's cover some commercial AutoML tools as well. The difference between these and the open source tools is typically to run one of the open source tools on a massive data set, you will need pretty powerful computers, GPU hardware, etc. However, with a commercial AutoML tool, you can just upload your data generally to a cloud provider, and they will manage all the computation for you. Some commercial AutoML tools include on AWS, SageMaker Autopilot for tabular data, and Recognition custom labels for image data. Google Cloud's cloud service also offers a nice AutoML suite that can handle image data, text data, or tabular data, as does Microsoft's Azure cloud platform. Finally, some other companies also offer AutoML offerings that may be able to run on multiple cloud platforms, including DataRobot and H2O driverless AI. The final set of tools we will briefly touch on are prediction APIs. One big difference between these and the previously mentioned AutoML tools are that these are not designed to be trained on your data. These are designed to allow you to access powerful, already trained models that may just happen to work for your use case. For example, if you're trying to detect objects in images or faces, Recognition offers a nice pre-built set of models that are very good at detecting almost any face or most common objects. Likewise, Comprehend, another tool offered by AWS, is a tool for text data that can detect things like sentiment, neutrality, basic text features that are just universal to language and that it doesn't necessarily need to be trained on your particular data set to do well on. Now let's talk about another AutoML tool that will be the focus of this tutorial. It's called AutoGluon, and it is mainly focused on deep learning and automating parts of the deep learning process, although it extends far beyond just deep learning models. The source code is available on GitHub, so you can run AutoGluon yourself on your own computers, and you can modify it as you see fit. There's a bunch of documentation and nice tutorials on the website linked below for AutoGluon. The overview of AutoGluon is as follows. Its main goal is to enable easy to use and easy to extend AutoML for tabular, image, and text data. With AutoGluon, you can quickly prototype accurate ML solutions in just a few lines of Python code. AutoGluon remains highly customizable and controllable by you, so not only can you modify the source code, but even within the library, you can modify many things, such as what metric AutoGluon should optimize for, how long it should run, how many compute resources it should be using, what kind of models should it be considering, should it distribute its computation across multiple machines, up to how it should pre-process data and sort of very fine-grained operations. You can really customize it to your heart's desire. You can even add your own custom models into AutoGluon, and it will automatically train and tune them along with its built-in models. AutoGluon allows you to leverage automatic hyperparameter-tuning, model selection and ensembling, neural architecture search, and data processing, which is one of the most overlooked parts of the ML process in other AutoML toolkits. AutoGluon allows you to easily improve existing modeling pipelines that are not even in Gluon or MXNet or anything. You can improve any model that you currently have using AutoGluon through its advanced HPO, aka hyperparameter optimization functionalities. These are different than standard hyperparameter optimization tools because AutoGluon supports multi-fidelity hyperparameter optimization methods like hyperband that can be much more efficient than hyperparameter optimization methods like Bayesian optimization, which require you to fully train models in order to assess how good their current hyperparameter values are working. Finally, AutoGluon offers a number of built-in tasks, meaning these can be addressed. You can train models for these tasks in just one line of code, and you can predict new data given a trained model for these tasks in just one line of code. These include predicting columns of tabular data sets, so classification and regression problems, classifying images, detecting objects in images, or classifying text, sentences, documents, paragraphs, etc. or even data sets that have multiple text fields. So for example, you might have a data set with 2 sentences, and the goal is to say how similar are these 2 sentences. AutoGluon is very easy to use. Here's all the code you need to train and use a model. Inside this code, especially the fit call in line 2, AutoGluon automatically does the following behind the scenes. It pre-processes the raw data. In this case, this is tabular data, so we have data in a bunch of columns. It'll identify what kind of data, what kind of variables are being stored in each column. It'll identify what kind of prediction problem this is. Is the column you want to predict contain discrete values or continuous values, i.e., is it classification or regression? It'll appropriately split the data, for example, into training or validation sets, or a k-fold split where there's multiple training and validation splits to help reduce variance in the learning process. And it will train and tune a bunch of individual various models, then create an optimized ensemble out of these models that outperforms any of the individual models. To give you a sense of why you should care about AutoGluon, I want to first talk about some benchmarks that we ran. Here we ran 2 sets of benchmarks on tabular data sets coming from the AutoML benchmark, which has been proposed by others as a standard benchmark to evaluate AutoML systems. It contains 39 data sets from OpenML. In each data set has 10 training and test splits, meaning there's actually 390 prediction problems in this benchmark. Previously, H2O performed the best by a slim margin over other AutoML systems. The second benchmark is a set of 11 prediction competitions taken from Kaggle. Most of these were proposed in a blog post from the Google Cloud AutoML tables team, where they proposed these as a good suite of tasks to evaluate modern-day AutoML tools. The nice thing about this benchmark is these are really realistic modern-day applications of supervised learning because they are directly being uploaded by companies that have real business use cases for the resulting models. Another nice thing about this benchmark is the evaluation metrics are very real-world motivated, and each is tailored to the particular business use case which generated the data. So these are not, just all being measured by accuracy or something simple like that. Each contest really has a specific metric that is designed by the organizers of the contest so that the resulting models that do well under that metric will truly be useful to them. Here we are comparing the tools I talked about before against AutoGluon on these Kaggle competitions. So each row shows one competition, the names on the y-axis. The colors in black are the competitions that are binary classification, in purple, multi-class classification, and in orange, regression. And on the x-axis, what we are showing is the rank achieved on the leaderboard by each system. So what does this mean? So what we did is we trained every AutoML system on just the raw data of the competition with a 4-hour time limit. And then we used the AutoML system to submit predictions to Kaggle, which Kaggle then evaluated on some private subset of the provided test data and provides a score. This score can then be directly compared with all the human data science teams as well as the other AutoML systems to see how well these AutoML systems do against each other, but also against human data scientists who are presumably experts. Of note here is that AutoGluon, shown as the star, outperformed most of the other AutoML tools on most of these data sets. So here, a percentile rank of 0.9 means this tool outperformed 90% of human data science teams that had submitted to this competition. Of particular note is the fact that AutoGluon actually outperformed 99% of the data science teams on 2 of these competitions, BNP Paribas and AutoGroup. And this is just after being trained on 4 hours on the raw data from these competitions, whereas presumably these human data science teams spent many, many weeks or months even, submitting models, resubmitting models, iterating on this process. So that's pretty cool. Another comparison was run on this AutoML benchmark of 39 data sets from OpenML. Again, we're showing each row is one data set. In black are binary classification data sets, and in purple are multi-class classification data sets. This benchmark did not contain regression data sets. Here we plot the loss on the test data, which in this benchmark the authors chose to have be AUC for binary classification, so area under the ROC curve, and log loss for multi-class classification, which measures not only how accurate your predictor is, but also how calibrated. Here we divide the loss on the test data achieved by each system divided by the loss of on the test data achieved by AutoGluon. So we're normalizing each system against AutoGluon. So AutoGluon here would always achieve a score of 1 on the x-axis. So systems to the left of 1 outperformed AutoGluon, meaning they achieved a smaller loss on the test data on this particular data set than AutoGluon. As you can see, there's very few systems to the left of AutoGluon on most of these data sets. And when they are, most of the time, they're very barely to the left. So AutoGluon really is outperforming most of these other tools on most data sets. Here we showed the same sort of results in a different format. That makes it perhaps a little more easy to digest. So here we're talking about the AutoML benchmark again, those 39 data sets from OpenML. Here each AutoML system was run for just 1 hour with a 1 hour time limit. These are all run on the exact same hardware, the same cloud instance, each system just running on one instance that's only running that AutoML system and no other processes, and only running one data set at a time. The columns of this table include the AutoML framework. Wins here means the number of times this system beat AutoGluon. Losses means the number of times this system was less accurate than AutoGluon. Here times corresponds to data sets. Failures means the number of data sets where each system failed to produce predictions for whatever reason. It could have just refused to handle this data set, or maybe it threw an error, some kind of exception while running, either during training or during inference. Champion measures how many times was this system better than all of the other AutoML systems combined. Average rank here measures if we rank the systems on each data set based on their accuracy and then take an average over all data sets. That's what average rank is. Average rescaled misclassification rate measures the error rate on each data set averaged across data sets with some normalization to ensure data sets where the best models only get 50% accuracy and or in data sets where the best models get 99% accuracy are sort of equally weighted in this benchmark. And finally, we also just show the average training time, because even though we impose a 1 hour limit on these systems, some of these AutoML systems do not exactly obey that 1 hour time limit. For additional benchmarking results, please see our AutoGluon tabular paper below, which covers the design of the AutoML system for tabular data. But going back to this benchmark, what we can see is that AutoGluon really outperformed each system significantly in a head-to-head comparison over these 39 data sets. Of particular note is the champion column following AutoGluon. This means AutoGluon outperformed all of the other AutoML systems combined on 17 of these data sets. That means in hindsight, had you run all of these AutoML systems one by one and then chosen the best one of them on the test data, which you wouldn't even be able to do in practice, you would still usually be worse than AutoGluon. So what's the difference between AutoGluon and other AutoML tools for tabular data? Like all of these existing AutoML frameworks I talked about, and there's many others. One key difference is many of these prior works viewed AutoML solely as cache, or combined algorithm and hyperparameter selection, where here algorithm is used interchangeably with the term model. This means these tools spend a lot of time searching for the best models, and they only do a little bit of model ensembling, and they put a little bit of effort into, say, data preprocessing. But the bulk of their training time is really spent training models under tons of different configurations in an effort to find the best. AutoGluon instead relies on strategies that data scientists use to win Kaggle contests or prediction contests more generally, such as model ensembling via multi-layer stacking, very careful data pre-processing, repeated data splitting to reduce variance in the fitting process, e.g. through k-fold bagging, which you may have heard of. And it places a much greater emphasis on modern deep learning techniques, which some of these other AutoML systems for tabular data totally ignore. One crucial thing that I mentioned before is you would hope an AutoML system just gets better the longer you run it for. If you just leave your computer, you would hope it keeps getting better. However, we noticed that some AutoML systems don't actually reliably get that better when run longer. So here we compare the 1 hour run time of different AutoML systems versus the same AutoML system run on the same data for 4 hours. Here we're showing results again for the 39 AutoML benchmark datasets. And we count how many times the 1 hour variant outperforms the 4 hour variant, how many times it's worse than the 4 hour variant, or on how many datasets is it equal to the 4 hour variant in terms of performance, roughly equal, of course. And so here we see that AutoGluon is, the 1 hour variant is only better than the 4 hour variant on 5 datasets, but the 4 hour variant is better than the 1 hour variant on 30 datasets. In contrast, none of these other AutoML tools is able to reliably improve their performance from 1 hour to 4 hours nearly as consistently. This is because these tools use hyperparameter optimization and cache extensively, and this search process is very prone to overfitting. That means if they search over tons of hyperparameters, using their validation data over and over again to choose which hyperparameter values are the best, they tend to find hyperparameter values that may just spuriously seem better than they actually are on this particular validation data set. Now let's talk about image classification with AutoGluon. So the goal of image classification is you're given an image and your goal is to assign it one of a few labels. Possible labels, I should say. For example, here we have images of clothing items, and the goal would be to classify what kind of clothing item this might be. And the basic type of data set formats, one example of a data set format that you can easily handle in AutoGluon is you could just have a bunch of folders. Each folder would be the name of one of your possible labels or classes, and the files in the folder would be your images from this class. So really, this is a very organic structure that you might already have on your computer. And to run AutoGluon on this data, you don't need to do anything else. Here's just how easy it is to run AutoGluon on such image data stored in this format, or we support a few other formats. Again, you see it's really easy to run AutoGluon, really easy to evaluate it on some test data. In contrast to tabular data, AutoGluon's fit for image data will run slightly differently. Again, it will preprocess the raw data and split it into training and validation sets. Here, it may also optionally apply some data augmentation to artificially enlarge the training data available to train models. This is because for image data and also for text data, oftentimes we know what kind of benign transformations of the image or the text should not change its labels. For example, if I just minorly rotate an image or translate it, presumably the underlying label did not change. And so we can use these kinds of strategies to greatly increase the size of the training data set. Optionally, AutoGluon will load an appropriate pre-trained model from some other libraries called GluonCV or GluonNLP, depending on if we're working with images or text. For example, a ResNet, a residual neural network for classifying images, YOLO3, a popular object detection model, or the popular BERT transformer model for text. So this pre-trained model has already been trained on some other data set. Then AutoGluon will suitably modify this pre-trained model's network architecture so that it's appropriate for your prediction task on your data. For example, the pre-trained model may have been trained with 1,000 classes of animals, say, and your goal is to classify clothing categories, which never appeared in the pre-training data set. So the models, at the very least, the model's output layer needs to be changed to reflect the fact that you're now only trying to predict 4 classes, and they may be totally different, belong to totally different categories. Then we will train this resulting neural network on your data using what's called transfer learning or fine-tuning. And this process can optionally leverage multiple GPUs, as these models tend to be quite large. We will repeatedly train many models under different hyperparameter configurations to find the best hyperparameters for these models. And you can optionally distribute this hyperparameter search over many machines for increased coverage of the search, or just to run it more quickly and get a high quality model in less time. You can optionally finally retrain models on the full training and validation sets, and also construct a more accurate ensemble of multiple models. This is, again, something that's not offered in many AutoML tools that try and automate deep learning, but it can really help you boost accuracy in a practical application. Here we show some results running AutoGluon's image classification module. Here we ran it on 4 Kaggle competitions, and again, we are showing the percentile rank on the leaderboard. So what percent of data science teams, human data science teams, in these image classification competitions was AutoGluon able to outperform just training on the raw data. So here, to produce each result, we only needed under 10 lines of code. And on each competition, shown as one row in this table, you can see that AutoGluon did pretty well. And one 15%, one 12%, one 9%, one 3%, meaning it outperformed 96% of data scientists in the dog breed identification competition. For more information, check out this blog post linked below covering additional results from this evaluation of AutoGluon's image classifier. Finally, you can also hyperparameter-tune any model with AutoGluon. So not just MXNet models, not just neural networks, really any model that has some hyperparameters, or even any Python code in general that has some notion of performance can be tuned using AutoGluon. And you don't really have to change your code at all. You just add a simple Python decorator, and AutoGluon will automatically start tuning the arguments of your function. You just need to point it to where the performance is basically being recorded, and that's all it needs. And what are the search spaces it should search over for each of your arguments. It implements numerous hyperparameter optimization algorithms, including random and grid search, Bayesian optimization, as well as advanced hyperparameter optimization methods that are known as multi-fidelity methods, meaning they operate on proxy measures of performance, such as, for example, if you're training a neural network, you could measure the performance of the neural network after just a little bit of training as a proxy for how well this neural network might do at the end of training. And by leveraging such proxy, these multi-fidelity hyperparameter optimization methods are able to find hyperparameters much faster than the aforementioned methods that require you to fully run your training jobs before you can report the resulting performance and move on to trying new hyperparameter configurations. Finally, again, you can distribute these hyperparameter optimization jobs across multiple machines. So even here, just tuning your own function, you can write your own function just on one machine, and you can then install AutoGluon on these multiple machines, and it will distribute its hyperparameter optimization to tune the arguments of your function just by you providing the IP addresses of all these other machines. Here's an example of the custom hyperparameter tuning. You have this dummy train function here that takes in some arguments, keyword arguments specifically. So here we have args, it has keyword arguments LR, maybe that stands for learning rate, and say batch size. Here it just prints these out, so it doesn't do anything. And then this function will report its accuracy. And then all you have to do to modify this function to be tuned by AutoGluon is you add this ag.args decorator. You specify search spaces for each of its arguments. In this case, batch size will just be a static value, and learning rate will be tuned between as a real valued hyperparameter between an upper and lower bound. And then we can just start tuning this function to find the best values of these hyperparameters. And beyond this, and beyond what will be covered in this tutorial, AutoGluon can do a lot of other things. For example, it can do neural architecture search, as I mentioned before, to find good neural architectures for your particular data set, so you're not constrained by what people have invented before in terms of neural network models. And it can also distill large model ensembles, which tend to be the most accurate models. They tend to be really unbeatable in terms of accuracy, but they tend to be slower for inference and more memory intensive and cumbersome. You can distill those large but accurate models into fast, cheap, single models that still retain a lot of the accuracy benefits of those big ensemble. So here, over a bunch of data sets, this bottom plot here, We first trained AutoGluon's large ensemble model produced by AutoGluon's tabular prediction module to achieve some accuracy. That's shown as the black dot. And then we trained a bunch of individual models. These are shown as the green dots. So we trained neural network, light GBM model, cat boost, random forest models. Those are the green dots. And then we used our distillation functionality where we train a copy of these same models. So the resulting model has the same inference time as the original versions of these models, but the performance of these distilled models is much better because they're trained to mimic the predictions of the teacher model, which in this case is, again, AutoGluon's big ensemble that's produced by default from the tabular prediction module. And on the y-axis, we're showing the accuracy achieved by all these models. And on the x-axis, we're showing the inference latency, how many seconds it took to produce each prediction from these models. And you can see that comparing each model type going from red to green, the distillation process really greatly improves the performance of this model without adding additional inference time or complexity. Also, we trained other AutoML tools that do ensembling, like H2O and AutoScikit-learn. And these tended to be less accurate than AutoGluon. These numbers here are all averaged across a bunch of data sets, by the way. But so these models on average tended to be less accurate than AutoGluon, which is not so surprising given the results I presented before, the full AutoGluon ensemble. But more noteworthy is actually our individual distilled models could be made to be more accurate than these full AutoML libraries that are using ensembles, even though our distilled models are just single models. And so that's shown as that red dot, the topmost red dot there is just a single model. And so here, you can check out this paper linked here for more information about this distillation process, which we'll briefly cover in the tutorial. So it's important to say who AutoGluon is not for yet. So this tool is really designed just for standard supervised learning, meaning non-standard ML problems cannot really be tackled with it. For example, if there's mismatch between your training data and the future data you'll be expected to predict on, AutoGluon has no way of knowing this, and it will probably not do well on your future data. This often happens if there's underlying confounding in your data or selection bias. Likewise, it's not designed for data that has dependence, such as time series data. It's really designed for standard supervised IID data sets where each observation is independent of the others. Likewise, if you have domain-specific constraints, such as fairness constraints that require some domain-specific knowledge, such as what are sensitive features, what features should we be cautious about, etc., there's not really an easy way to encode that into AutoGluon at the moment. And finally, if you have data that has, say, censoring or some other quirky properties, again, this is not the tool for that, at least as of this moment. Finally, for unsupervised learning or exploratory data analysis, we encourage you, again, to use third-party tools. These are critical parts of a good modeling pipeline, but they really should be done prior to using AutoGluon, which is mainly just designed for the supervised learning aspects of the pipeline. And finally, we want to just emphasize that this is mainly intended to be run on Linux, and it's only supporting Python. A lot of the functionality does, in fact, work on Windows and Mac, but it's just not rigorously tested there. The roadmap upcoming for AutoGluon development in the coming months our goal is really to become the most useful open source library for machine learning, meaning it's the most accurate and the fastest, but it's also the most user-friendly and easiest to use, meaning you can write as little code as you want and just get accurate models, but also if you want to customize it, you can as to your heart's desire. And we also want it to provide the broadest set of ML capabilities across all kinds of different data types, different kinds of prediction tasks beyond just standard classification and regression. And we're working on being able to handle multimodal data that might contain tabular, image, text features all in the same data set. We're working on particular tricks that you might use if your test data are available ahead of time, semi-supervised learning, trustworthiness like interpretability or uncertainty estimation to help you place more trust in the resulting trained models, as well as more prediction tasks, as I mentioned before, such as image segmentation, multi-label prediction, few-shot learning, etc. And our final goal starting right now is we're really trying to actively grow the open source community. And so if you're using AutoGluon and you find there's some problem that it doesn't tend to do that well on, that you think other people have the same, they're facing the same issue, we really encourage you to push a fix to GitHub and just propose a fix, open a pull request. And the relevant references for this tutorial that I encourage you to look at include this paper covering the design of AutoGluon, particularly the tabular prediction model for tabular data, the AutoML textbook from Frank Hutter and others that is a really comprehensive overview of the field of AutoML, covering it from many different perspectives. Dive into deep learning if you just want to learn the fundamentals of deep learning is a really nice textbook that has hands-on examples, code, great math explanations, and text. So it's really the first textbook that combines code, math, and text explanations of concepts all into one textbook in a very elegant way. And finally, there's a survey paper linked below that just compares empirically a bunch of other AutoML tools on different kinds of data sets, and there's many such survey papers. So this is just one of many that we think was one of the more well-done papers.